So in this lecture we will give a couple of examples of covering spaces. So we start with the standard example of covering of a circle with the real line. So this is given as x is taken as a real number and it is wrapped around the circle by exponential of 2 pi I x, where this I is a complex number, square root of -1. And you can see this is a wrapping around a circle because you know that the exponential of 2 pi I x, you can write it as cosine x plus I sine x, where I is square root of -1. Now to show that this is a covering, we have to take some point z in S1 and then take its neighborhood and show that the neighborhood is trivially covered. So we have to formally define the neighborhood. So neighborhood we define as u of z as S1, and then you take minus z out. So you can see in this circle everything gray is the neighborhood of point z, and we have taken this point out. So this point is out. So now pre-image of u of z with z as exponential of 2 pi I x, this is given as a union of intervals. So this z, this corresponds to some coming from some x here which gets mapped here, and then there are series of such x's. So say x1, x2, x3, x4 and so on. All these are getting mapped to z via this map exponential of 2 pi I x, and we have to show that this neighborhood is trivially covered, and this is shown from this interval of length 1. So say this x1 corresponds to 1, x2 corresponds to 2, 3, and then you can have here x0, and you can keep going down with x minus 1, x minus 2 and so on. So we will chalk out one of the intervals like this to show, so this n is an integer, to show that actually this is a trivial covering. So say a pre-image of minus z is some point here, and we put it as say y, and then you start taking the neighborhood. So this is the neighborhood here. So this portion gets lifted right here, and then you have this top portion which will get lifted all the way to the next point which gets mapped to minus z. So now we want to talk about this portion. So this portion gets lifted from here so now you can see how this unit interval, so you see the length of this interval is precisely 1. So this unit interval here is getting mapped homeomorphically onto this interval, and you can keep doing the lifting. So this is just one interval, and this is disjoint from the next one because these this unit interval will not get mapped to minus z here. So this you see it is skipping one of the points. So that is why you will have this trivial covering. So you will have this covering, this is disjoint from the next one which will go all the way to some point here, and then it will go all the way up to this some point here, and it will keep going up. So next is disjoint interval will go from here, 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 all the way here. Then next disjoint interval. So you will have this as many integers there are, those many trivial coverings we will have for S1. So there is a homeomorphism from each of this interval to u of z. So now we want to cover this circle S1 with another circle S1. So for this we have this map which is degree n from going to z to the n. We will say this is a covering. So to show this is a covering, we first need to take a point z in S1, find its neighborhood and show its neighborhood is trivially covered. So we will show that there are n sheets. So you set u of z as S1 minus z. So for example, we want say point -1 here. So to have neighborhood of u minus 1, we have to take 1 out from here. So you take 1 out from here. So this entire thing now with this point is out of S1. This forms the neighborhood of u minus 1. And then you lift this up. So you take the nth roots and you lift this up. We will you get n pre-images of minus z which partition the space into n parts. Now essentially everything is from roots of unity. So for every this Z lying in S1, you can just rotate this cover by appropriate angle to get the corresponding pre-image for whatever Z or minus Z you have. So essentially everything boils down to roots of unity. So we think in terms of roots of unity. So these are the n roots of unity from 0 to n minus 1. So obviously for 0 you will have 1. So we will form an n-fold cover of u minus 1. So with precisely root of unity missing in the cover. So here we will form a 3-sheeted covering. So you will have this map Z to Z3, or here we are taking this as minus 1. So this 1 is missing here. So 3 roots of unity would be, one cover is just this 1 corresponding to this. The second cover is right here. Now I'm going to plug in, this was corresponding to k equals to 0, now corresponding to k equals to 1. So you have exponential of 2 pi I over 3, and then we will have right here, this will be corresponding to this point, missing point is corresponding to exponential of 2 pi I 2 over 3. So these now we have 3 covers for this neighborhood of u of minus 1. So this is a 3-sheeted cover, and this 3-sheeted cover we got from 3 roots of 1. So essentially for any z mapping to z of n, you will get n cover. So essentially you start with taking roots of unity for that cover, and then you rotate that cover appropriately, because you can take this 1 to any z here. So this 1 can be taken to any z in this circle by appropriate rotation by some angle theta. So say this, you have to take it to this point z, you just rotate by this angle theta. So you can rotate the cover to get the required point. So now we have a covering of this projective plane with Sn. So to get to projective plane from sphere, what we do is we identify the antipodal points. So that is how we construct the projective space. So a point y in projective space Pn has 2 pre-images, minus x and x in S of n. So say these 2 antipodal points. So this line goes through the origin. You identify them to get a point y in the projective space, and these points lie in some Sn. So now to get neighborhood of this uy to be mapped to this here, so this is a degree 2 map, because you will have precisely 2 neighborhoods mapping to u of y, neighborhood of u of x and neighborhood of u of minus x. So we need to concretely construct these neighborhoods. So for this we connect these 2 points. So we have connected these 2 points, and then draw a plane orthogonal to the line connecting these points. So we are going to draw a plane perpendicular to these 2 points, and this plane is going to cut the sphere into 2 parts, upper part and lower part. So you will give us 2 hemispheres which act as neighborhood of u of x and u of minus x, which will map homeomorphically to u of y, because identification map to u of y gives us the projective space. So this is the plane which is cutting the sphere. So you have a top part of the sphere and the bottom part of the sphere. So this top part of the sphere is neighborhood u of x, the bottom part of the sphere is u of minus x, and these 2 map homeomorphically to u of y. That is just because of the construction of the projective space. You just identify points, so there is not much to it. So now we want to end this lecture with a non-example. So say you have this set in R2 which you are projecting to a line. So this here xy, this gets mapped to x. So we are saying this is not a covering space. So that is because you say you take an interval AB right here, and you take its pre-image. So this pre-image, you get this rectangle which is a connected set. Now we want the pre-images to be locally trivial. So that is, you have to have a large number of disconnected sets here. So disconnected, so but this is a connected set. You cannot make it into a disjoint union of open intervals. So this is entirely connected. We cannot make it into a disjoint union of open intervals. So we cannot provide a locally trivial cover because there are no copies of interval here. This is just one connected piece. So this is not an example of a covering space.